Okay, once again, thank you guys for coming today again on this, I think quite a nice, cool Tuesday evening. Thank you so much for your time. I hope today's class will be interesting for you guys. So to follow up from where we left the last time, we were at the selection operation or operator. So what we have is, just to recap, R is supposed to be your table. And I am going to be selecting items from the table based on a certain condition. So let's say if this is the table R, sorry, I'm trying to admit people at the same time. And based on a certain condition, it will then output that of the schema, or rather another, I would say it can be considered to be like a view. Considered to be like a view, which is of the same schema as that of the original table. So in this aspect, let's say how I got from here to here, the exact condition that I'm using is where A3, which is this current table here, is going to be bigger than or equals to 0. So when A3 is bigger than or equals to 0, I have the following so-called rows, which is this row and this row. These two rows are bigger than, have A3 values bigger than 0, and so they'll be in a way selected out to form this view over here. Similarly for this, it looks at the columns A2 and it looks at the column A2 and looks for the value of A2 having either A or B. And so these two rows will be then selected to form here. So that is a bit of recap for selection. And now let's look at this example. So I think last week there was some I think I mixed up the two statements. So the first one is when SID is greater than or equals to 4003, and this is how we will write that to be when SID is greater than or less than or equal to 403. So the table name is student, and I'm selecting the SIDs where it is greater than or equals to 403, which is this, and this. And if I want to find students that are not here, means they are not in this above relationship, so I can use the not operator on the condition. Alternatively, this is equivalent to, so these two are the same. I believe last week I went to swap the two statements. I think accidentally, yeah. So this is essentially what this slide is trying to say. Okay, and that was where we stopped at last week. And subsequently, and I believe a question was asked also on this slide, which I'll go through later on. The condition is attribute operator constant, or attribute operator attribute operator or attribute. My operator is a so-called comparison operator that looks like this, and they can also combine various terms as well. So in this case, we have in the previous slide. This is operator. Sorry, attribute operator with what's the term they use? Constant, with a constant. So this is what we have. Of course, we can also have attribute operator attribute. So for example, I can have doesn't make any sense here, but I can have let's say I have a rate in try 1 and I rate try 2. Then I can have a grade try 1 greater than grade try 2. For example, something like this. Yeah, so this is where attribute operator attribute comes into play. Excuse me. There was also a question on the order of attributes, or rather the order whereby they come in. So the top order is always the bracket, and then this is the subsequent orders that they come in. So of course, I think one of your colleagues pointed out earlier, is similar to C, and N is higher precedence and all. So it gives rise to this statement over here. So if we were to use the operators here, this would come in first. So followed by this. But then if you want the OR operator to come first, then we have to put it in brackets so that this entire thing will be operated first, followed by this one. So how this reads is that this will read like this. Okay, so this will read like SID greater than 4004 or grade less than 4 and gender less than 1. Okay. Okay with this? Okay, let's see. If we were to run this command, let's say SID less than 4004 or grade less than 4, I'm going to get SID. Actually, is now we come to this. It's actually easier to. It may be easier to look at this gender first. Okay, because yeah, so easier at least for me. So we know that gender must be less than 0, less than 1. Sorry, so it's this, and this, and the condition of SID less than 404 or grade less than 4. So I have less than okay. So this one will work. Okay, less than 404. This one will work. Less than 4. This one will work. Less than 404. This one will work. And the intersection between them will give us these two rows. And this is for this statement. If you are going with the former one whereby we don't have the brackets, what we'll be having is that grade is less than 4 and gender is less than 1. So grade less than 4 and gender less than 1 is going to be only Cathy. So grade less than 4, gender less than 1 is only going to be this person, and this or this happening will be this, because these three are also less than 404. So what will happen will be these 4 rows will be returned. So if I were to run this command, these 4 rows will be returned. If I was to run this command, these 2 rows will be returned. Excuse me. Okay. I hope this is clear. Sorry that my handwriting is a little bit messy, but I hope this is clear. But if you later on, maybe during the break or whatever, you go through this, you realize, oh, actually, yeah, quite interesting. Okay, good. Okay, let's go on. And then we are looking the next. So that the earlier one was on selection. So so actually, it's a very common, extremely common operator. The other very common operator is projection. So projection removes unwanted columns from the relation. So and many times, like you may have, columns that you do not need further down the road, and you would then, in a way, project out only the columns that you require. So for example, if let's say you have a very big database table of let's say a user, and you have name, you have address, you have phone number, and you have maybe gender, you have income, a lot of things. But maybe you only need the gender and the name. So you will just need to project these two out, and then you then do other operations based on this. It is extremely common. How this works is the following. So in this case, R is again our main table. The projection of column A1 on the table R will give only my column A1, which will give all my rows in A1, which is A, E, and F. Similarly, if I were to project A3 and A2 out of the column R, I'm going to get C, B, and C, D. Okay? C, B, and C, D. Notice that in this operator, the duplicates are automatically eliminated, so they are removed. So over here, when I project A3 and A2, A3, A2. So if I were to copy wholesale this, it will be C, 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 B, D, B. But this is duplicated with this. Excuse me. And so one of these will be eliminated. And this will then end up with what we see over here. Okay. Okay, good. Okay, let's look at an example. So right now we have both a selection and a projection. Yeah. So we are going to do in this scenario, we're going to do the selection first, followed by the projection. So let's do this together. So in the selection process, I'm going to ask for the gender, which is equals to 0, and the grade, which is 3 or greater. So it happens that in this segment of the database we're seeing, all the grades are 3 or greater, so everybody will be so we need to look at the second condition, rather the first one, which is gender equals to 0. So only this, and this will be selected from this operator. And then from then on, we are going to project out SID and SNAME. So only these two columns will be taken out. So in the end, we're going to have SID, SNAME, and 4001, 4002, 4004, Amy, Alice, and Kathy. So this will be the result of this query. Okay. Okay, good. So let's look at the next one. So that was, earlier one was, we first started with selection and then projection, and this renaming. So renaming is just a matter of renaming a so-called a new old table, or rather a table with a new name. It is strange, but this is in fact very important. Actually it is it's very strange, but this is actually a very important operator. Why? Because many times you need to join the table with itself, and you realize that in order to join it with itself, most often you need to rename the table into something, so as to be able to join it with itself. Else you can't do that. Yeah. So it is very strange, but this renaming operator is a very important operator. So this is how it looks like. So the new table, the new table name will be here, and the old table name will be here. Okay, okay. It will get clearer as we go along. Let's look at this. So you heard me talk about join a number of times. So join, So join. Let me talk about join a number of times. So today we'll be talking about the join operator. So in this case, I'm going to have, this is how the join operator works. In the first we have table R and we have table S, and the first step we do is a Cartesian product. First step is a Cartesian product. So you have, recall in the last lecture, we talked about Cartesian products. So the first thing we do is actually a Cartesian product between both table, let's say these are joined with S based on a certain condition. The first thing we do is actually a Cartesian product between R and S. So yeah, so between R and S, we do a Cartesian product, which is what you see over here. So let's say if we have AB and we have HC here, recall last week what we said is that every single row here will be joined with, or will have a corresponding, will end up with a corresponding relationship with every single row over here. So if let's say the cardinality of this is 2, the cardinality of this is 3, the resulting cardinality of this cross product is going to be equals to 6. Okay? So this is how this works now. So when this 2, this 3, the resulting will be 6. So the first step is we do the join of we do the Cartesian product. The second step is we do the selection based on this condition. So we have this Cartesian product that is being generated here. The second step is that based on this Cartesian product, we're going to select based on a certain condition. And this condition that we are doing will be in this situation, let's say B less than or equal than H. So for B less than or equals to H, we will look at this table and look at which are the tuples or rows that fit this condition. And the rows that fit this condition will be this one, this one, this one, and this one. So these will be the 4 rows that fit this condition. They will be, and this will be the output of my join. Okay. Okay. No questions so far. Okay, good. What was I going to say? So this is the first of the joins that we are going to encounter. So you realize that there are different types of joins. Yeah. So this is the, in a way, the one of the generic types of joins, whereby you're just joining based on a certain condition. Actually, it's also very, very common. Yeah, but you're just joining based on a certain condition. Let's look at one example. So we want to list all the colleges the students both can apply. And here it says that we want to project out only the ID and the name. So so a bit of a hint given to you already. We only want the ID and the name. So I'm going to do a high of the SID and also the R of S name. Okay. So so in the thing is we want to project out only these 2. So yeah. So we at least we know this is the sort of the outcome of it. So what we want is the complicated part is what is inside. So we probably need to do a join between these two. We need to how to say, we need intuitively, right? This is the minimum GPA that they accept. So this is the GPA that the student has. So when they can apply, what we are looking for is what are the records in R with a GPA greater than or equals to the minimum GPA of table S. Right. So this is actually what we want to find out. So once again, I say, let me see, is there a question? Okay, once again, I say, this is actually a joint between R and S, and I want to find out the GPA values of table R, where it's higher than the GPA, the minimum GPA values of table S. So this is a joint based on a certain condition, which also they call it a theta joint. Okay. So I'm going to R join with S. And my condition is my R dot GPA is greater than or equals to S dot minimum GPA. So yeah, let me write this properly. So this is how I would write my query in relational algebra. Any questions on this? Okay. Anybody need me to repeat again? All good. Okay. Good. Okay, I think everybody is getting it. Okay, let's look at the this answer. Yeah. So anyway, this is what we have here. So yeah. So let's look at another example. Return the course IDs where both where both student 4001 and 4005 are registered. We return the courses ID where both student 401 and 405 registered. Okay, so let's look at this for let's try to explain this in English terms. I want to find the course IDs where we have both 401 and 405. So in this, I think sometimes it's when you look at this is hard to say in English, but actually what I want to find is to find the course with both student 4001 and 4005. So essentially that is what I really want to do. So let's look at what we can how we can do it. So the first step that I can find is this. So right now I notice that this is my course enrollment table. On this side is my student ID, and on this side is my course ID. So this is where the strange thing actually comes in, where it is actually this renaming is very important, because it is very likely that I'm going to somewhere down the road I will need to have a R join with myself, but I actually cannot do that. Because because it is not legal in relational algebra to join with myself in this manner. So I need to rename myself first. So I will hence need to rename myself with a row. Let's say I rename it to R1. And then I will join it with my new so-called new renamed table, which is R1. And what do you think is the condition that we should have? Okay. The first step is that let's look at the first step. Let's look at the first step, which is let's look at where the course IDs are the same. Okay, so let's look at the first step. Let's look at the ones whereby I join myself and I find which are the ones with the same course IDs. So let's look at R.CID equals to R1.CID. why am I doing this very strange step? I'm actually trying to find out in this table, right, when I join with myself, or rather, when I do this join with myself, right, when I do this Cartesian join, I'm trying to find out which are the rows whereby I have both course IDs to be the same. So this is what I'm trying to achieve. This is the first step. Okay, let's go in to see the first step right now. So this is the very first step. So let's imagine that, let's say if I'm doing the join, this is what I wrote earlier. R1 is, let's say R1 is these two columns. R is these two columns. Let's look at, the first step is actually a Cartesian product. So I'm going to Cartesian product each one with each one. And then after that, I will then do the selection based on this condition. So notice that in this output, right, I already have both of these to be the same already. Okay, both of these to be the same already. Okay. Okay. So what I'm trying to do is I want to find which are the course IDs with both of these to be the same. And then the next step that I want to do is I want to find which one is both has the first ID to be 401 and which one has the second person to be 4005. Okay. Ken, am I is it clear? Do I need to repeat myself, or it's fine? Okay, I'm going to assume that it's fine. So the first step is me doing a join with myself, and then thereafter I want to find which is the row there with my same course ID. So this is the resultant. The second step is from this table, I will do a selection based on r.sid equals to 4001 and r1.sid equals to 4005. And this will make me end up with just these two rows. This is the second step. Okay, and then after this, the third step is then because I only need the course ID. So the third step is I do a projection of r.cid over this thing, and then it will give me only the numbers 25 and 28. Is that clear for everyone? Okay, why do we need good, there's a question, very good. Why do we need to do RIC when we can do equals to 401 and R1? Oh, if we do that, right, if we Jiao Wei raised up a very good question. Why do we need to join these two, do a equivalence of r.cid and r1.cid first? So if we don't do that, wait. I think your question is not how to put it. Your question is you mean to say when I do the join is r dot SID equals to 4001 and R1.SID equals to 405. Okay, so I think that's what you mean. So what if we were to carry out this relationship, right? What we will have is that we will get, let's say, 401 as also 11, and so this is like that. And then I also have 4005. 405 also take another module. Okay, then mine is okay. It's 25. So this row will also be written. So if we don't do the equivalence, right, we will return this row because we didn't. So because initially it's a so if you're looking at just this, right, the first step, right, of this join is a Cartesian product. So a Cartesian product, it will have all rows of one joined with the other rows. So if you carry this out, you will end up with a lot of rows that look like this. So 401, right, it also took cos 11. Yeah. So it also took cos 11. Yeah. So if we are doing good, yeah. So you will also end up with this row, which is yeah. So not the yeah. We will need to join them based on the class ID. But it's a great question. Yes. Okay with this. Yeah, so this is a little bit convoluted, but it's a very good question to see how this join, a very good example to show the relationship, or rather to show the join, the selection, the renaming, the projection. So it actually shows everything at the same time. Another question: can we combine the then condition in step 1 with step 2? So step 1 is this one. Step 2 is a selection. Let me think. I'm doing a selection. I got the feeling that you can do that. I have the feeling that you can do that. I have a feeling that you can do that. I will check for you, but I have a feeling that you can do that. I, however, may not recommend that because it is quite. Oh, sorry. It was a private question. So a question was asked: can we combine step 1 with step 2? So this is step 2. This is step 1. Can we combine these two steps? Meaning that we put in this condition also within our join condition. So I actually have the feeling that we can do that. I have the feeling that we can do that. Yeah. So and I also have the feeling that if we were to do this in a proper SQL so-called database, that may be what it may do. So it may get all the 401s out first. So I'll just have 3, which is 11. It's a good question. It's a very good question. 11, 25, and what's the third one? 28. And then I'm going to get the next, which is 405, 4005, 4005, 25, 28. We do the Cartesian product over here, and then they carry out only this slash operator. Yeah. So it is, definitely able to do that. But I I think but at least to me lah, it's very 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 hard to understand Yeah, it's theoretically you can place a very complicated issue. Yeah, correct. Yeah, and it will be very hard for me to understand and very hard for me to mark. So you can but I think uh, uh, maybe maybe and also very easy for you to make mistakes. So I think yeah, you see what is best. You see what is best. But in theory, yes, you're able to make things convoluted. But I think there's a yeah, will be quite easy to make mistakes. Yeah. Yeah, it's good. It's good. It's good. Yeah. Okay. It's good. So let's go on to the next. So I went through this already, so I don't need to go through this. Okay. So right now we are at natural joints. Natural joint is similar to joints, but then the condition is that they are going to enforce equality on attributes with the same name. So if you have columns with the same name, they will be eliminated and they'll be joined together. So in this, for example, in this scenario, I have AB and I have BC. So B is my common condition. So then when I join it together, I will have A1 here, 1, and X, and A1 with Y. So notice in this scenario, right, this gets eliminated because there is no corresponding 2 value, and this gets eliminated because there's no corresponding 3 value. Okay, so this is that of a natural join. The duplicate attribute here will be attribute B. Okay, but this is a good and a bad point of natural joins. So you lose these conditions that you don't have a corresponding entry to. So for instance, like over here, we have 4 lecturers here. Let's say Prof. Edward does not give any lectures for that trimester. When I do the join, he will be missing from my so-called resultant table. Yeah, so that is the downside of this. Okay. Later on, we'll be looking at outer joins, which will help us to resolve this kind of issue. So it will help us to eliminate this condition. So if you compose, we can compose, because as what your colleague mentioned, we can place a very huge and complicated condition, but it may make it very convoluted and also very hard to check. Yeah. And of course, parentheses, brackets will be precedence, and if in doubt or unless very sure, use brackets. So quite common to use brackets. Okay, so the natural look the same as the Cartesian join. Let me see. Cartesian join. Okay, Cartesian join. Okay, there's Cartesian product, which is the times. And what we did earlier was the theta join. So did I call it Cartesian join? It should be theta join. Or yeah. So this one should be called a theta join. And the main reason why it's a theta join is because there's usually a theta condition here. Yeah. So yeah. So maybe that will yeah. Hopefully that will clarify a bit here. Yeah. So yeah. So usually there's a this is in underscore. So this is actually like in small caps like that. Yeah. And these are usually what we call theta joins. Yeah. So when you do a natural join, right, then there's no theta condition. So yeah, maybe you want to take note. Yeah, there's no theta condition. So it is expected, not expected. It is it is recognized that there's no condition. So when you see that, you're just joining based on the common attribute, common column name. Okay, let's go on. Okay, so yeah, so I talked about this earlier. So the next thing we are going to talk about is relational algebra. Let me think. What time is supposed to be the break? Not yet, right? I think not yet. Okay, let's go through this. The break is supposed to be 50 minutes, is it? Yes, okay. We'll break in about 5-10 minutes time. Okay, let's go through this relational algebra division. Okay, so let's say R has two attributes, A1 and A2. And I have and S has only one attribute, A2. There is a ability for us to, in a way, divide between two tables, R divided by S. And when R divided by S, actually is quite amusing in this case. Yeah, so the schema will be the attributes of R minus the attributes of S. I think there's a missing minus attribute. I'll add that later on. Yeah. So R1, R2, and is A1, A2, and this is A2. So when I divide, I will only be left with A1. Because yeah, we would not end up with that attribute that S has. And the interesting thing is, let's say if this is XY, I can only take the rows with both X and Y's, or rather with all the corresponding columns in S, in order for me to output a value here in my division operator. Okay, so yeah, so it's what this one. R must contain all the values in A2. Okay. Okay, good. Let's look at the next one. So let's look at this example. So I have R, excuse me, R, which is A1, A2, and A3, and this is table S with A3. So when I do the division, my resultant will only have A1 and A2 because it must so A1, A2, A3. If I do the division, I will end up with only A1 and A2. So that's why A1 and A2. Okay, and then for this, I will have to find which are the rows with column with a value of C, all the values that are in A3 of table S. So here, here, here. And so the resultant will be, so these three tables here, we don't have this in our resultant division operator. And so this will end up with just AB, 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 DP, and AE. Okay. Okay, let's look at another example. Okay. Okay, so right now I have R divided by S prime. And right now, of course, the resultant has only A1 and A2 because A3 is there. I want to look at which are the rows with C and F together. So let's look at just the ones with C, which is here, and the ones with F, which is here. So one easy way to think about it is that if we remove this one, we use the intersect operator. So which are the columns that intersect between these two so-called views? So in these two views, A and E are common over these two, and B and D are also common across these two. So this will get over here, and so our final output is BD and AE over here. Okay. Okay, let's look at one more. Okay, so over here, I have R and I have S double prime. A3 is the common column. So I'm going to end up with only A1 and A2. So notice that right now I have four individual, four distinct unique values in A3. So I'm going to end up with four unique values, four unique views or tables of A3 with value of C and F and G and H. So C will be this. Let's do 1, 1, 1 over here. F will be 2, 2, which is 1. So this is 1. This is 2. This is 3. And this is 4. So this totally doesn't have. And what we do is we will then take the intersection of all four of these so-called tables. So the only one that appears is AE, which is here. And so AE appears here. So this is then the resultant of this division operator. Okay. And the final one I have is R with S triple prime. And so this is an operator with how to say, with two columns. So the resultant column that will be remaining will be just A1. So in a way, I want to look at all the so-called all the rows with BC over here. So actually, there's only these two rows in BC, and AD will then get returned over here. Okay. If let's say I have EC here, EC, my intermediate will have AB, AD, and this is for BC, BC. And let's say if I have an EC here, EC, EC will have just A. And if this is the scenario, I'm going to have just A written here. Okay. All okay with this? Okay, very good. Okay. The use of this division operator. Yeah. So the division operator, for this is one example of the use of this division operator. So I want to return the students of all the students who registered, the students that registered for all the courses in a certain table. So let's say these are the three tables here. I want to have the students that register for all. So if I do the division operator, I'm going to find out the who registered for both 11, 25, and 28. So 11, 25, 28. 11, 25, 28. So 401. This one, 402 did not register for 25, 28. So no. So no. So 404, 11, 25, but no 28. None. So the resultant of this will just be 401. Okay. Okay. Very good. Okay. Then I think now is a good time to take a very short 10 minutes break. So let's do a 10 minutes break. I have to I have to drink some water. I'm sorry, because my throat is a little bit dry. So I'll be back in about maybe just give me about 5 minutes like that. So I'll be back in about five minutes for any questions. But in the meantime, please take a 10 minutes break. Thank you. It's 9:30 and we will start. Okay, so thank you all for coming back and staying with us through the evening. So before the break, we were talking about the division, how we want to use the division operator to return the students that register for the courses in the school. So for example, if there's a table here, we want to find out who are the people that always have a corresponding entry for the CID in their table. So if we were to use the division operator, we will be able to find out that in the division of R divided by S, we will only end up with the SID column. And over here, we will only have 401 because only this 401 has these three corresponding entries over there. I lost my chat box. I'm going to go back to that. Oh, I didn't. Did I share my screen? No, I didn't. I'm sorry. Yeah. So please let me know if I forget to share my screen or I do strange things like that. So yeah, fortunately, yeah. So please let me know. Yeah, thank you. Let me see if if anybody is waiting at the room. Yeah, everyone just trying to ensure that there's nobody waiting outside. Okay, good. Nobody waiting outside. Okay, so that was what we did before the break. And after the break, sorry, not after the break. Right now, we're going to be looking at this, the motivation. So earlier I mentioned that if we were to do the this is the natural join, so there's no theta condition. The natural join, we would be missing certain items. So for example, Prof. Edward, he does not have any any lecturing so-called appointments, for example, in a certain trimester. If I were to do a join, I would miss him out totally here. Maybe something that we don't want to have. So maybe we don't want this. We don't want this situation. So the so-called the solution is then to we call them an outer join. So in the outer join, what will happen is that for notice the first thing we want to look at is that this then it is very similar to a natural join. So there is also a column that is the same. So that is the so-called the similarity. The column is the same. There is a column that is the same. If we were to do a natural join in this scenario, I'll join with S. What we'll end up with, we'll have A1 and then we have A3. So notice that our we will have dropped one column. And we only have one common value, which is C. So we will only end up with C, 3, and 11. This will be the only output out of our natural join if it's R joined with S. However, if we were to carry out a outer join, what will happen is that they will find that, oh, I have A and B here. I don't have a corresponding entry in my S. And so instead of dropping them, I'm going to add in the null values here. And correspondingly, on my left side, if it finds out that there isn't the corresponding values for D and E, I will still have this remain, and I will have null values here this time around. So this is the difference between the natural join versus the outer joins. Notice that we keep both columns. So we don't drop any columns in this outer join because you may end up with null values. Okay, I'm going on to the next one. So that, excuse me, there's a left outer join and there's right outer join. So there are times whereby you want to join it based on the so-called the left side, and some of it you join it based on the right side. Sorry, left side, some of it the right side. So in the left outer join, so we want to keep all the values in our left table, and so this is not seen and it will be dropped. So in left outer join, we keep the left table. In the right outer join, we keep the right table. So in the left outer join, we keep the left table. So the values here are kept, and so we have null values that are here, which is being eradicated. And this is the corresponding right outer join, whereby I keep my values in my right table, which is D and E, and I put in null values here instead. Okay. And in this scenario, we have both. This is both the left outer joins where we want to keep the values in our left tables. So I want to keep my values in my left table because I want to keep 12 Edward here. So I first do a left outer join between this table and this table. So when I do a left outer join, I'm going to end up with 101, 102, 103, 104 Edward, Radium, Gu, Liu, Fang, and I'm going to have now. This is going to be 102 is 25. This is going to be 28. And Liu Fang is going to be 11. Yeah, 11. Okay. And then, because if we were to carry out a normal join or even a right outer join here, it will be incorrect because then we will be eliminating this value here because we don't have a corresponding CID value here. So that's why we need to do another left outer join here to keep our left values. So to do when we do the left outer join here, then we have the C name. And this is now, because we don't have a corresponding value for now here. 25 is going to be C++, 28 is going to be OS, and 11 is DB. Okay. Yeah. So yeah, so this is how this left outer join works. Okay. Yeah, I need any questions so far? Okay, sounds okay, sounds good. So just a very brief summary in case you want to have a quick reference. So the first one is Cartesian product. So R times S, every value of the first table gets linked up with all the values in the second table, and correspondingly as well. So every row here will have a corresponding value here. Similarly, every row here will also have a corresponding value here. So if this is if this is 2, cardinality 2, cardinality 4, the cardinality of the resulting table will be 2 times 4, which equals to 8. Okay. Okay, very good. So theta join. So yeah, I just changed it, this to add in the theta. So theta join is there's a certain condition here. So you are joining 2 tables. Yeah. So but always there's a unique condition. There's a condition that you impose onto it. There's a condition that you impose onto it. So in this scenario, this is what we saw earlier. The condition is b less than or equals to h. So this is the condition. So this theta join. The third one is natural join, whereby you are joining based on the common column, and you're going to drop the common column, and you're going to just store all the values that occur in both columns, sorry, in both tables. So in this scenario, only the value 1 appears in both tables, and so only 1 will be so-called joined together. Okay. Okay, so far. Okay. And the last one is the outer join. So yeah, outer joins are so there are times whereby you want to retain the values in either your left tables or your right tables. The 4 outer joins will be returning in both. If you do a left outer join, you are retaining the left table. The right outer join, you are retaining the right table. So the so-called the strange things indicate left or right. Okay, very good. So this is again a repeat of what we mentioned. Can? Oh, okay. Okay, so far. Okay, if all is good, what we would like to do now is I have shared a set of new slides on on the Moodle. So they are the exercise for relational algebra. So actually, I would really like any questions? All okay? So if there are no questions, I would really like you all to take a look at this exercise for relational algebra. There are some questions here, which I hope that you all hope it's not too late to do a discussion. But I hope yeah, just try to work out among yourselves or individually or something. So I will let's try this now. Let's try this to see how this works. I tend to like to do breakout rooms. No, that's not data. No lah, be on no. So I will try to do a breakout room. Maybe about 6 to 7 people per room. And the time now is 9:40, 42. Let's try to spend maybe I think 15 minutes on it. Yeah, and we come back at about 9:57. Okay, let's try to do that. We come back about 9:57. But in the meantime, I will be walking around the various breakout rooms. And hopefully, if there are any questions there, I will help to answer them. Okay. 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 So this set of slides, they are already on Moodle already. I just uploaded them during the break. So please go and download them. And I'll see you either in your breakout rooms or back at this room at about 9:57. Okay, thank you. See you soon. Okay, thanks for coming back. So let's look at the questions one by one.
He said thanks for coming back. Well,
Yeah. So sorry for that. Okay. Let's look at. Let's hope this works. Okay. So the first question. Let's look at. Let's look at the first question. The list of IDs for students of GPA are greater than 3.5. Okay. So firstly, there will be a section of GPA equals to 3.5, and I'm going to take it from which table? Probably the student table. Okay, so student table, and I only want to get my student ID, so I will have to do a projection of my student ID. Can okay, all good. Okay, let's look at this. So let's look at the second one. So the second one is list the ID and the name of students that are studying in a large high school. So it's actually when of my this greater than 1,000. So probably the table I'm looking at is again the student table. And I want to, in a way, select size of HS greater than 1,000. Okay, and I only want the ID and the name of the student. So ID and the name. So I'll be putting SID and S name. Okay. Okay, with this one. Okay, good. This one these two are still relatively straightforward. Okay, this one start to get a little bit. It's not difficult, but it's just very irritating because it's very big. So yeah, so I want to get the student ID, which is here, the student name, but I also want to have the applied college name, which is here, and also the state. So you can tell it's going to be a very irritating query because I need to join all three tables now. So with this thing, but the nice thing is that I can just do a very simple natural join. So I can do a simple natural join student. A lazy way is I can do a lazy natural join. Apply and college. Okay, and there is no actual condition. So there's no condition. I just need to project the student ID. So if I want to be specific, I can put student ID and student as name, their college name, and also the stat. Okay, so this is how the query or how the relational algebra will look like. Okay, so this is still somewhat straightforward. Okay, nothing. Yeah, pretty straightforward. Okay, let's look at the next one. So it starts to get a little bit complex, but still not too much. It just says that the colleges are located in so-called California. So it's still largely similar. So we can still do the 3 joins. Apply college. From here, I can just do a state which is the state equals to CA, and then I can do my projection like what we did in the previous query. Okay. Okay. So far, nothing too strange. It's just a typical application of the RA rules. Okay. So now, okay, students that applied for MIT or Cornell. So I'm going to do a so-called selection. Oh, sorry. So the name, the table that we are looking for definitely is applied, because no other tables allow us to do that. So this will be we know that this is applied, and then the CNAME will be equals to MIT or CNAME equals to Cornell. And then I'm going to project out my student ID. Okay. So again, nothing out of the theta work join with condition. Okay, so sorry, there's a question here. Yeah, I think the theta join would also work. Yes, that will also work. Yeah, yes, Mr. Zheng Yi. Yes, it will also work. Yes, Zheng Yi, it will also work. Yes. Thank you for your question. Yeah, so in this case, yeah, so you can just do a selection, and then after that do a projection of the SID, and that will be fine for this question. Okay, so far so good. So this is where things get a little bit complicated. So students that apply for both, students that apply for both MIT and Cornell. So if we were to use back our reasoning that we did in earlier, so I'm going to do a selection of CNAME equals to MIT and CNAME equals to Cornell. Apply, and I'm going to do a projection this ID here. Okay, so if we were to use back our reasoning from this part, this seems to be a reasonable relational algebra, but this is actually incorrect. Can anybody venture to tell us why, although it's really late in the evening? Yeah, Mr. Emil is very correct. It means that both conditions must be true, but it's impossible for both conditions to be true. Yeah, so both of these conditions can never be true. You can never have the name of this to be both MIT and Cornell. Okay, so it cannot be the case by both MIT and Cornell together. So the way to handle a situation like this, of course, we don't want to go into so-called a join. If you don't want to go into a join, you can actually do this. Or rather, let's do CNAME equals to MIT first. Apply, and I project out the SID, and then I do a CNAME equals to Cornell, and this is the SID of people that applied for MIT. These are the SID of people that applied for Cornell, and then I do a intersection of these two. Yeah, you can also duplicate first and join. I believe that is also acceptable. But I think this is one way that I think is more slightly more intuitive to me. But I think you can do the technique that we did earlier, whereby you want to have join between, so apply 1 and apply, and then you have SID from here equals to SID of here, and then you have C name of this equals to MIT, and C name of this equals to Cornell. This is also acceptable. That's what Lim Ziyi, Miss Lim is trying to say. Okay. So both this is fine. Both are fine. Okay. Okay. I may overrun for 1 or 2 minutes, so sorry about that. Okay. So, but I'll try to finish as soon as I can. Okay. So the students that did not apply to Stanford. So of course, the natural way to look at it is that is a C name not equals to Stanford. Apply. Project out the ID. Yeah, this is definitely the natural way to think about it. But actually, this is not correct again. Yeah, because this is going to so let's say this guy 123, he applied for Stanford and Berkeley, but this will come up this row as well. So 123 will also return. Okay, so this is incorrect relational algebraic expression to. So I want to finish this before time. So yeah. So the right way to look at this is actually to get a projection of all my students minus of the projection of the people that applied to Stanford. And this will give me the IDs of people that did not apply Stanford. Okay. So this is how it's supposed to be. Okay. So I'm sorry that the last few minutes and I overrun by 1 minute. So let's take a stop here, and I will still stay online. If you have any questions, please feel free to ask. I will go through this in a bit more detail again in the next session, which is this Thursday. But in any case, sorry that I overrun by about 1-2 minutes. Thank you so much for your time this evening, and yeah, hope you guys enjoyed the class today. No problem. Good evening.